Deep in the southern Ural Mountains, where the continental plates of Europe and Asia grind against one another in a geological embrace that spans millions of years, there lies a place where the compass needle spins in a confused, drunken circle. This is not a malfunction of the instrument, but a testament to what lies beneath the soil. We are standing at the edge of a magnetic anomaly so potent that it was known to ancient travelers and cartographers long before the first shovel struck the earth. This is Magnetnaya, the magnetic mountain, a geographical freak of nature composed almost entirely of pure, high-grade iron ore. But today, the mountain itself is largely gone, hollowed out and consumed by the industrial leviathan that sits at its feet. In its place stands a sprawling, smoking metropolis of steel and fire that defies the very scale of human comprehension. This is the Magnitogorsk Iron and Steel Works, known simply and affectionately by those who work its blast furnaces as Magnitka. It is not merely a factory, it is a city-state of heavy industry, a monolithic altar to the Soviet era's obsession with production, covering an area so vast that it possesses its own internal railway system, larger than the public transit networks of many European capitals. To understand Magnitka is to understand the absolute limits of industrial engineering when it is pushed to the breaking point by political will and the terrifying necessities of war. This facility was not born from a gradual economic evolution. It was willed into existence in the 1930s, carved out of the frozen steppe by a workforce that consisted of idealistic volunteers and forced laborers, all digging the foundations in temperatures that frequently dropped to -40 degrees Celsius. They were building what was promised to be the steel heart of a new empire. As we look out over the skyline today, dominated by the towering silhouettes of the blast furnaces and the endless forests of smokestacks, we are looking at a machine that never sleeps, a beast that consumes trainload after trainload of raw earth and breathes out the skeleton of the modern world. The scale here is so immense that standard metrics fail to convey the reality. The plant does not just consume electricity, it devours enough power to light up a major metropolitan area. It does not just use water, it drinks rivers. The central conflict here is a permanent, violent war between the chaotic forces of thermodynamics and the rigid, unyielding will of the engineers who attempt to harness them. It is a battle fought at 1600 degrees Celsius, where a single miscalculation does not result in a reprimand, but in a catastrophic steam explosion or a breakout of molten metal that can vaporize a human being in a fraction of a second. This is a world of heavy shadows and blinding light, where the air tastes of sulfur and metallic dust, and where the ground vibrates with a low-frequency hum that settles into your bones and never truly leaves. We are going to strip away the facade of this industrial giant and crawl inside the machinery. We will trace the journey of a stone from the moment it is ripped from the earth to the moment it emerges as a pristine sheet of automotive steel, exploring the metallurgy, the chemistry, and the sheer brute force required to transmute matter on this scale. If detailed technical breakdowns of heavy industrial engineering and extreme manufacturing interest you, subscribe. I have got more of these coming. But before we can understand the steel, we must understand the fire that births it and the terrifying complexity of the systems designed to keep that fire from consuming everything in its path. The journey begins not at the furnace, but at the marshalling yards, a sprawling labyrinth of tracks where the raw ingredients of steel making arrive in quantities that stagger the imagination. Steel is, at its most basic theoretical level, an alloy of iron and carbon, but you cannot simply throw rocks and coal into a pot and hope for the best. The process requires a meticulous, almost surgical preparation of materials. The iron ore, which arrives as dusty, reddish-brown rocks, is rich in iron oxides, iron atoms bound tightly to oxygen atoms. The goal of the entire facility is to break that chemical bond, to strip away the oxygen and liberate the pure metal. But the ore is too fine, too inconsistent to be dumped directly into the blast furnace. If you were to pour fine sand into a ventilation pipe, you would choke the airflow. The same principle applies here. The furnace needs to breathe. To solve this, the ore is sent to the sintering plant, a facility that is effectively a massive, continuous bakery for rocks. Here, the fine ore dust is mixed with limestone flux and coke breeze, fine particles of coal, and ignited on a traveling grate. Imagine a conveyor belt the width of a highway lane, moving slowly through an ignition hood where gas burners scorch the surface. The heat creates a wave of combustion that travels downward through the bed of material, fusing the dust and rocks into large, porous clinkers called sinter. This sinter is the bread of the blast furnace. It has the structural integrity to support the crushing weight of the charges above it without crumbling into dust that would suffocate the fire. But the sinter is only one half of the equation. The other half is the fuel, and for a blast furnace, regular coal simply will not do. Coal contains impurities, sulfur, phosphorus, volatile gases that would ruin the quality of the iron, making it brittle and useless. Furthermore, coal is too soft. It would be crushed into a powder by the thousands of tons of material stacked inside the furnace stack. The solution is the coke oven battery, a terrifyingly inhospitable section of the plant where coal is baked in the absence of air to create coke. The coke ovens are narrow, deep chambers lined with silica brick arranged in long rows like books on a shelf. Coal is dropped into these chambers and heated to 1,100 degrees Celsius for 18 hours. Because there is no oxygen inside the chamber, the coal does not burn. Instead, it sweats. The volatile gases, the tars, and the oils are driven off, captured, and piped away to be refined into chemicals, leaving behind a hard, porous gray rock that is almost pure carbon. This is coke. It is incredibly strong, capable of bearing the weight of a skyscraper of ore, and it burns with a clean, intense heat. But the hidden cost of this solution is the environment on top of the battery. The lid men who work here walk on the roof of these ovens, surrounded by leaking gases and radiant heat, wearing wooden clogs because rubber soles would simply melt and fuse to the deck. It is one of the most hazardous jobs in the metallurgical world, a place where the atmosphere itself is flammable. With our sinter and our coke prepared, we move to the heart of Magnitka, the blast furnace. Standing at the base of one of these towers, you are struck by the sheer verticality of the structure. It rises nearly 100 meters into the air, a complex network of pipes, catwalks, and gantries wrapped around a central pressure vessel. This is not merely a chimney, it is a countercurrent chemical reactor. The principle is elegant but violent. Solids go down, gases go up. The sinter and coke are carried to the top of the furnace by skip hoists, small rail cars that climb a steep incline, dumping their loads into the charging hopper. To visualize the scale, imagine a small dump truck driving up a roller coaster track every few minutes, 24 hours a day, for 10 years straight. The materials pass through a system of bell valves designed to create an airlock so that the pressurized gases inside the furnace cannot escape while the raw materials are being added. Inside the stack, the alternating layers of coke and ore slowly descend, descending into hotter and hotter zones. At the bottom of the furnace, the Bosch, massive compressors, blast preheated air through nozzles called tuyères. This air has been heated to 1,200 degrees Celsius in towering stoves that stand like sentinels next to the furnace. When this superheated air slams into the coke at the bottom of the stack, it ignites instantly, raising the temperature to over 2,000 degrees Celsius. This is the inferno. The coke burns to produce carbon monoxide, a gas that races upward through the stack, stripping the oxygen atoms from the iron ore as it passes. This is the chemical reduction. By the time the ore reaches the bottom, it has been stripped of its oxygen and melted into liquid iron. The remaining rock and impurities float on top of the iron as slag. It is a continuous, roaring process, a controlled explosion that never ends. The pressure inside is immense, several atmospheres of hot gas pushing outward against the steel shell, which is lined with refractory bricks and cooled by thousands of liters of water circulating through copper staves embedded in the walls. If the cooling water were to fail, the steel shell would soften and rupture within minutes, unleashing a river of liquid fire. Every few hours, the furnace must be tapped. This takes place on the cast house floor, a cavernous, dark space illuminated by the orange glow of the runners. The keeper of the furnace uses a remote-controlled drill to bore a hole through the clay plug at the base of the hearth. The moment the drill breaks through, a jet of white-hot molten iron and slag erupts from the furnace, flowing down a refractory-lined trough. The heat is physical, a tangible weight that presses against your chest. The air shimmers so violently that vision becomes distorted. The sound is not a roar, but a heavy liquid hiss, punctuated by the crackle of escaping gases. This is the pig iron, the crude product of the blast furnace. It is rich in carbon, roughly 4%, which makes it brittle. You could not build a bridge out of this. It would shatter like glass under impact. It is merely the intermediate step. The molten iron is directed into torpedo cars, massive cigar-shaped rail wagons lined with firebrick, capable of holding 300 tons of liquid metal. These cars act as giant thermoses, keeping the iron molten as it is transported across the vast internal rail network to the steel-making shop. Watching these torpedo cars move through the Russian winter is a surreal experience. The exterior of the car is warm enough to melt the snow falling on it, creating a perpetual mist that shrouds the train. The locomotive struggles for traction on the icy rails, hauling thousands of tons of liquid death through the center of the factory. The logistics of Magnitka are a delicate ballet performed by heavy machinery. If a train derails, or if the scheduling is off and the iron sits too long, it will begin to solidify inside the torpedo car. This is a skull, and removing a 300-ton skull of frozen iron is a nightmare that involves jackhammers, explosives, and weeks of lost production. The system relies on constant movement, a heartbeat of logistics that cannot be allowed to fibrillate. The destination for these torpedo cars is the Basic Oxygen Furnace, or BOF. This is where the alchemy happens, where brittle iron becomes flexible, durable steel. The vessel itself is a pear-shaped pot, suspended on massive trunnions that allow it to tilt. It is 3 stories tall and lined with dolomite bricks. The torpedo car tilts, pouring its glowing cargo into a charging ladle, which is then lifted by an overhead crane. This crane is a monster, capable of lifting 400 tons, the weight of a fully loaded jumbo jet. The operator, sitting in a cab high above the floor, must have the dexterity of a watchmaker. He lowers the ladle and tips it, pouring the liquid iron into the mouth of the converter. Scrap steel is often added first to act as a coolant and to recycle old metal. When the molten iron hits the cold scrap, sparks fly upward in a cascade that looks like a heavy artillery shell detonating. Once the vessel is charged and returned to an upright position, a water-cooled lance is lowered through the mouth of the converter, stopping just a few meters above the bath of molten metal. This lance blows pure oxygen at supersonic speeds directly onto the surface of the iron. The effect is instantaneous and violent. The oxygen reacts with the carbon in the iron, burning it off as carbon dioxide. This is an exothermic reaction. It generates its own heat. The temperature inside the vessel spikes, boiling the metal. Impurities like silicon, manganese, and phosphorus are oxidized and trapped in a layer of lime flux floating on top. It is a ferocious process, lasting only about 20 minutes. Think of it like blowing bubbles into a glass of milk with a straw, except the milk is liquid steel, the breath is supersonic oxygen, and the bubbles are burning carbon monoxide. The vessel vibrates, the building shakes, and a roar fills the hall that renders speech impossible. At this stage, the steelmakers take samples, dipping probes into the boiling bath to check the chemistry. This is the critical moment. Too much carbon and the steel is too hard, too little and it is too soft. They add ferroalloys, vanadium for strength, chromium for corrosion resistance, tweaking the recipe with the precision of a master chef but using shovels and chutes instead of spoons. When the composition is perfect, the converter tilts and the steel is tapped into a ladle, leaving the slag behind. We now have liquid steel, 1,600 degrees Celsius, ready to be cast. But the question remains, knowing what you now know about its real-world production bottlenecks and extreme hazards, do you think the massive capital investment in this facility was worth it? Share your thoughts below. The molten steel in the ladle must now be solidified into a usable shape. In the old days, they poured it into individual molds to make ingots, a slow and inefficient process that resulted in significant waste. Today, Magnitka uses continuous casting machines. The ladle is lifted to the top of the caster, pouring the steel into a tundish, a bathtub-sized reservoir that acts as a buffer. From the tundish, the steel flows through a copper mold that is cooled by high-velocity water. The steel freezes against the walls of the mold, forming a solid shell, but the center remains liquid. This strand of steel is pulled downward by rollers, curving gradually until it is horizontal. It is like squeezing toothpaste from a tube, but the toothpaste is red-hot metal that solidifies as it moves. If the shell breaks, a breakout, liquid steel spills into the machinery below, destroying millions of dollars of equipment and shutting down the line for weeks. It is a constant game of thermal management, balancing the speed of the casting with the rate of cooling. The resulting product is a slab, a massive rectangular block of steel, glowing red, weighing 20 or 30 tons. These slabs are the currency of the steel trade. They are stacked in the yard, radiating heat for days, waiting for the final stage of the journey, the rolling mill. The rolling mill is where the brute force of the facility is most visible. Let us look at the Mill 5000, one of the crown jewels of Magnitka. The 5000 refers to the width of the steel sheet it can produce, 5,000 millimeters or 5 meters wide. This mill produces the thick, high-strength steel used for bridge decks, oil pipelines, and the hulls of icebreakers. The slab is first reheated in a walking beam furnace until it is a uniform 1,200 degrees Celsius. It glows a soft, translucent yellow. It slides out of the furnace and onto the roller table, a long runway leading to the mill stand. The mill stand itself houses two massive work rolls, cylinders of hardened steel that do the actual flattening, and two even larger backup rolls that prevent the work rolls from bending under the pressure. The force applied here is astronomical. The mill exerts thousands of tons of pressure, squeezing the thick slab into a thin plate. Think of it like a steamroller flattening a piece of dough, but the steamroller weighs as much as a battleship. When the steel hits the rolls, there is a thunderous crash, followed by the deep, agonizing groan of the motors as they fight the resistance of the metal. High-pressure water jets blast the surface of the steel to remove scale, oxidized metal that forms on the skin, creating an explosion of steam that envelops the entire stand. The operator, sitting in a pulpit overlooking the line, controls this violence with joysticks, reversing the rolls, bringing the steel back and forth, reducing the thickness with each pass. The floor plates rattle. The air smells of ozone and hot grease. The radiant heat from the steel plate, which is now 50 meters long and growing, can be felt through the glass of the control room. It is a display of power that taps into something primal. This is not the clean, silent precision of a microchip factory. This is the heavy, dirty, loud reality of the material world. After rolling, the plate passes through a controlled cooling unit where curtains of water quench the steel at precise rates to lock in the desired crystalline structure. The metallurgy is determined here. Cool it too fast, and it becomes brittle martensite. Cool it too slow, and it becomes soft ferrite. The goal is often a complex bayonetic structure, tough enough to withstand the impact of an iceberg or the pressure of a deep-sea pipeline. But beyond the machinery, beyond the chemistry and the physics, there is the operational reality of Magnitka. We must talk about the environment. For decades, the city of Magnitogorsk lived under a perpetual shroud of black snow. The unfiltered exhaust from the blast furnaces and the coke ovens rained down particulate matter on the playgrounds and the parks. The snow would fall white, and within hours it would be covered in a layer of gray soot. The children of the city had higher rates of respiratory illness. The workers faced chronic health issues. In recent years, massive investments have been made in filtration systems and electrostatic precipitators to scrub the exhaust, capturing tons of dust before it leaves the stacks. The sky is clearer now, but the legacy of pollution remains in the soil and in the collective memory of the population. And then there is the winter. Operating a facility of this size in the southern Urals poses unique challenges. When the temperature drops to -40, lubricants turn into gel. Conveyor belts become stiff and can snap. Hydraulic lines burst. The iron ore in the rail cars freezes into a solid block that cannot be dumped. To combat this, the plant has massive thawing sheds, garages heated by gas jets, where entire trains are parked to defrost before unloading. The sheer energy cost of fighting the Russian winter is a line item on the budget that would bankrupt a smaller company. The workers, wrapped in layers of wool and fire-resistant synthetic fabrics, move like deep-sea divers through the freezing mist. Their eyelashes frost over, but inside the plant, they strip down to t-shirts as they approach the furnaces. It is a life of thermal extremes, moving between the Arctic steppe and the tropical heat of the production line multiple times a day. The logistical network required to keep this city within a city alive is staggering. The internal rail network handles more tonnage annually than the entire national rail networks of some small countries. There are hundreds of locomotives, thousands of wagons, all moving in a synchronized chaos. A delay in the delivery of scrap metal to the BOF shop ripples backward, forcing the blast furnace to slow down, which in turn forces the coke plant to adjust its heating cycles. The inertia of the system is massive. You cannot simply turn off a blast furnace. If you stop the air blast, the burden inside will cool and solidify into a monolithic rock that effectively destroys the furnace. It must run continuously, day and night, for campaigns that last 15 or 20 years. The commitment to the fire is absolute. As we assess the legacy of Magnitka, we must look backward to look forward. During the Second World War, known here as the Great Patriotic War, this plant was the forge of victory. When the factories in the West were overrun or threatened, production was shifted to the Urals. It is said that every second tank and every third artillery shell fired by the Red Army was made from Magnitogorsk steel. The famous T-34 tanks, which drove the invaders back to Berlin, wore armor plate rolled on these very grounds. The Sword of the Motherland monument stands on a hill overlooking the city, a massive statue of a worker handing a sword to a soldier. It encapsulates the identity of this place. It is a warrior city, where the weapon is the ladle and the enemy is the impossible quota. Today, Magnitka faces a new battle: the global market. It is no longer enough to simply produce tonnage. The steel must be high quality. The automotive industry demands ultra-high-strength steels that are light enough to improve fuel economy, but strong enough to pass crash tests. The energy sector demands pipe steel that can withstand the corrosive sour gas of the Arctic fields. Magnitka has had to pivot, investing billions in modernizing its rolling mills, installing vacuum degassers to remove the tiniest impurities, and automating its control systems. The rust is being painted over, replaced by digital sensors and automated logic controllers. Yet, despite the modernization, the soul of the place remains unchanged. It is still a place where humans confront the elemental forces of nature. The Man of Steel is not just a moniker for a dictator, it is a description of the character required to endure this environment. The workers here possess a specific kind of pride, a stoicism born of long shifts and dangerous conditions. They respect the molten metal, for they know it has no conscience. A splash of steel does not care who it hits. Safety protocols are written in blood, lessons learned from accidents that left empty spaces in the locker room. The balance sheet of Magnetka is complex. On one side, there is the undeniable environmental toll, the scarred landscape, and the hard lives of the workers. On the other side, there is the sheer miracle of production, the ability to take the dirt of the earth and turn it into the skeleton of civilization. Skyscrapers, bridges, ships, cars, washing machines, the material basis of modern life flows from these tap holes. The magnetic mountain may be gone, dug up and smelted down, but its legacy is spread across the entire planet, embedded in the infrastructure that holds our world together. This is the reality of heavy industry. It is not clean, it is not quiet, and it is not safe. It is a roaring, dirty, magnificent beast that demands respect. It is the foundation upon which the digital world rests, for you cannot build a server farm or a smartphone without the copper, the steel, and the aluminum that come from places like this. Magnetka serves as a reminder that we are still a species that relies on fire and stone, masked by a thin veneer of silicon. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.